Let's have a little bit of fun today, just doing some experiments on the bench. I decided to get out my old curve tracer kit, and I did a video on this. You can buy the circuit board and the kit online on eBay, although this was a couple years ago, several years ago that I did this, so I don't know. You would have to look online, but I know that the parts are still available. And I just took one of those 2N2222 transistors from a previous video that I did on differential amplifiers and thought we would just play around and look at some of the effects that we have to account for when working with bipolar junction transistors and semiconductors in general, that some different things that you can see. Now, specifically with these transistors, the reason we use a curve tracer is to be able to see how the transistor operates through various voltages and base currents and so forth. The two things I want to look at today and demonstrate is the effects of temperature change on a transistor and a function called the early effect. E-A-R-L-Y, and that's capital E because it's actually not early as in, not late, but it's actually named after the individual, James Early, that actually discovered this characteristic of a transistor. So the first thing we'll talk about is that. Now, what you're looking at is a curve trace of a 2N2222 transistor. And if we look at the XY axis on the scope, and ignore this line, this sloped line is actually an artifact that's being generated by the curve tracer. This is a low cost unit. This is not the same as my big curve tracer. This is just a little kit. So just ignore that, but the rest of it works perfectly. And what we're looking at is each one of these lines represents a certain base current that's being applied from the base to the emitter. So it would be IBE. So I, current from the base to the emitter. And for each base current, we're sweeping with a sweep signal from 0 volts up to just a little bit under 10 volts. So when we apply a certain base current, so for instance, step number 2 is 24 microamps. So by applying 24 microamps of current from the base of the transistor to the emitter of the transistor, we're outputting this little amount of collector to emitter current, if that makes sense to you. So for instance, if I look here, if I put 24 microamps of current onto the base of the transistor, and at about 2 volts, which is right around here, right? You can see that we have about, what is that? Let's expand it a little bit. We can see that we have about 7 millivolts. So 1 millivolt equals 1 milliamp. So at about, when we put 24 microamps of current into the base, we get about 7 milliamps of emitter collector current. Okay? And we can actually do the math, which is a simple division problem, and we can determine the gain, or the beta, of the transistor, the forward current gain, at that particular voltage and that particular input current. But if you notice, as I increase the amount of voltage between the emitter and the collector, so that would be VCE, something strange happens. With higher base currents, you could see the problem gets worse and worse. But notice you don't get a linear output of current. In other words, the current actually starts rising as we increase voltage. And this effect that you see that makes this line slope like this is called the Early effect. So this is the effect that James Early discovered in a transistor. Now, it's a very small amount of current difference, but that change in current actually is additive in the circuit, and it can actually affect the performance of the circuit in some instances. It's slight, but it's there. Also, another interesting thing is if you took this and you took a ruler and you drew a straight line like this with each one of these all the way back. Here's 0 volts in this down here in the corner. If you drew it clear off of the scale and drew them all together, they would converge at 0 volts at a certain point. And that convergence there, or 0 amps, I'm sorry, 0 current, at the point at which all of those converge at 0 current, that negative voltage, that's called the early voltage. You can actually use that early voltage to determine an effective resistance, okay, that would act like that's the amount of resistance that you have in parallel with your emitter resistor, if that makes sense. So early effect does have some effect on the circuit depending on how it's biased and how it's working. The other thing we're going to talk about is temperature change versus beta. Now this transistor has been on the curve tracer for a while now, so it's kind of stabilized. It's like at its ambient operating temperature. But what happens if I change that temperature? So let's try two different things. First, we're going to cool it down with this freeze spray, and then we're going to heat it back up with a heat gun. And let's see what happens to the gain of the transistor. So first we're going to chill it. What happens? Almost instantly. You can see now the transistor is less efficient. In other words, with the same amount of base current, I get a lower amount of collector current, or emitter collector current. So temperature greatly affects the gain of the transistor. That's why the design of the circuit, how you design a transistorized circuit, is very important, because these things, if not dealt with properly, can become a big issue because now you're trying to chase a moving target, right? These are the kinds of things that we're trying to avoid when we design amplifiers, especially preamps where you're dealing with really small signals. Conversely, if I take the same transistor and I heat it with a heat gun, you can see the gain goes up substantially, and eventually the transistor will saturate. In addition, the early voltage gets more prominent. You can see as the thing cools back down, that early voltage, actually that slope changes a little bit. So they all interact. So because of the effect of the early voltage, or the early effect as they call it, whenever you see a specification in a data sheet for a transistor, not only do they give you the base current and they give you the emitter collector current, but they also tell you when they're telling you the beta, or the gain of the transistor, they're telling you that at a specific voltage, and that's why. So the reason that we see that in a spec sheet they always specify the gain at a certain VCE is because the gain actually changes with VCE, and it's because of the early effect. So at lower base currents, you can see it has almost no effect, but as we go more into that, you can see it gets more prominent. And if we drove the base currents even higher on this, which I don't want to do that on this little transistor, this would get increasingly worse. So hopefully that kind of explains a little bit of what the early effect is. Now the early effect is characteristic. It can be confusing. It has to do with the junctions at the base of the transistor, the way it's made. That junction width actually controls how a transistor conducts like this. And that junction width actually, at least its effective junction width, it's not physically changing, but the effective junction width varies with VCE. And it's just a characteristic of transistors. It's something that happens. They refer to that, and they refer to that early voltage as VA. So, in case you're wondering. But anyhow, I just thought it would be interesting. I was playing around with this curve tracer just to see if it still worked and everything from sitting, and thought this little quick video would be interesting to look at and just to see some of the changes. And these are the kinds of things that we try to deal with some of the designs that we use in the amplifiers. So when we talk about the constant current sources and current mirrors and different things like that, and thermal coupling of the transistors and all that, all of those techniques are used to counteract some of these types of effects. There are a lot of other ones in there, for instance Miller capacitance and things like that, but we're not going to talk about those. Okay, one last thing I feel like I should bring up before we close out this video is a third characteristic. So we looked at temperature, how temperature affects the gain of the transistor and the performance of it. We looked at the early effect and how that affects the gain of the transistor based on the VCE. And one last thing I wanted to mention is the FT, or transition frequency of the transistor. Now, just like collector to emitter voltage can affect the gain, it's only slightly, you can see, but it does. The frequency of the signal that you're applying to the transistor will also do that. So as you go from DC up in frequency, as the frequency increases, the gain of the transistor decreases. And this has to do with the amount of time that it actually takes a transistor to go from one state to another, like from turning off to turning on, or turning on to turning off, or from changing from one voltage level to another. And that actually, once you reach a certain point where the frequency of the signal is faster than the amount of time it takes to turn the transistor on and off, what will happen is the transistor will no longer have any gain. Okay? And we call that point where the transistor becomes unity gain, we call that its transition frequency. So the closer we get to that transition frequency, the lower the forward gain is going to be of the transistor. Now, some transistors have very high transition frequencies, even up into the hundreds of megahertz. But some have lower frequencies, like some of the early silicon transistors, like the original very first 2N3055 that came out. Some of them only had less than a 1 megahertz transition frequency. And even the newer ones only had a couple of megahertz. And everybody's real familiar that works on amplifiers of the MJ series, the big TO3 transistors, like the MJ21193, MJ21194, MJ, what is it, 20 something or other. There's a whole bunch of them. All of them have transition frequencies somewhere between 2 and 4 megahertz. Which is relatively low compared to some other transistors out there. And we've done videos about special transistors that get around that to have very high transition frequencies, like when we talk about the LAPT type transistors or the ring emitter transistors, and we did a few videos on those, but I thought I should just add that in there. So 3 big factors that affect the performance of a transistor. Okay, the early effect, temperature change or temperature stability, and transition frequency. And a lot of the things that you see that we do or that manufacturers do when they're designing, for instance, an amplifier, because we talk about amplifiers on this channel, are things to get around those issues, to make them either negligible or reduce them to a point where they have a minimal effect. All right? So the takeaway from this video should be those 3 things, I hope. But it's just something interesting to know, because I know I get a lot of comments of people just, saying, you're nitpicking, this is stupid stuff, audio fool, they use that word. Well, if you look at how a transistor works, these are very real things. Some of them, depending on the design of the circuit, are negligible. Other times they actually have a real effect that you have to take into account in your design. And so just thought I'd show that to you, and hope it was interesting. It was a lot of fun for me. So as always, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care. Bye-bye.